Hello, I am Professor N.B. Hulle from G.H. Raisoni Institute of Engineering and Technology. In this video, we will solve this particular problem and we will calculate the current in the branch AB for this particular network. Branch AB, here is A and B. We are interested to calculate directly current in the 10 ohm resistance. Now here we will follow the steps. Step number 1. Remove the load resistance and redraw the same circuit. As per the Thevenin's theorem, first step, we will remove the load resistance, we will redraw the same circuit and we will calculate the parameters stepwise. This is the first step. The circuit for first step will be something like this. Here is the terminal A and this will be the terminal B. Here it is 4.5 volt. This is plus minus 3 ohm, 6 ohm, 6 volt plus minus. This is 6 ohm plus minus 6 volt. Here we are interested in the calculation of the VTH. Second step. We are interested to calculate VTH, that is Thevenin's voltage. Now, to calculate the VTH of Thevenin's equivalent voltage, we have to calculate current in this branch because we will travel from B towards A. We will use this path, maybe this path or maybe this path. Use any path. The current will be the same. But I will follow this path. We need to know this current. Now here, to calculate current in this branch, we have to calculate current in both loops. Now here in this case we can use any method. There are so many methods are there. We can assume this is as one node, this is ground node, this is branch 1, branch 2, branch 3. We can use the nodal analysis. This is loop 1, loop 2. We can apply the KVL to the loop 1, loop 2. We can find out its current. Otherwise, we can use the direct inspection method. I will use here the direct inspection method. And directly we will find out the currents I1 and I2. We are interested in I2. And that we will use its values. Now here its matrix will be something like this. We have the two variables which are I1 and I2. We are interested in I2, which is equal to constant. Direct inspection method. Now here in this case we have the matrix will be something like this: R11, R12, R21 and R22. This will be the matrix, impedance matrix for the two loops. R11 is the resistance of the first loop. This is first loop. Its resistance will be 6 plus 6, that is 12. Diagonal elements are positive again. Then R22, resistance of the second loop. This is second loop. Its resistance will be 6 plus 3, that is 9. This is 10. And remaining elements are negative, means R12 and R21. That is resistance which is common for the second and first loop or first and second loop. First and second loop, second and first loop, means common resistance is the 6, means this value will be minus 6 here, minus 6 will be here. Then calculate the value of the constant 1, C1. If we are traveling with the direction of the current, to calculate C1, I will use this calculation of C1 here. If we are traveling with the direction of the current, we are traveling with the direction of the current for loop 1, negative to positive, plus 6. Then positive to negative, which is minus 6, which is equal to 0. We are traveling in this direction, negative to positive plus 6. Then positive to negative, which is minus 6, 0. Means constant 1 is 0. Then constant C2, we are traveling with the direction of the current, negative to positive, which is plus 6. Then for loop 2, we are traveling positive to negative, which is minus 4.5, which is equal to 6 minus 4.5, which is equal to plus 1.5. This constant is 1.5. Now here, in this case, if we know this matrix, directly we can calculate its currents I1 and I2. More, here we are interested in current I2. We will calculate both. I will use the calculator here. For this calculations, mode. Then I will go to mode again, mode equation number 1, variables 2, then A1 12 is equal to sign B1 minus 6 is equal to sign C1 0 is equal to A2 minus 6 is equal to then 9, which is equal to C2, which is 1.5 is equal to. The X is, or the first current is 0.125 amperes. I1 is 0.125 amperes. Then I2 0.25 amperes. This will be 0.25 amperes. Now if we know the currents I1 and I2, now we can find out its value of the VTH, which is equal to modulus value. We will travel from B towards A. Now we need the polarities. Now look at this I2 is flowing downward. That's why polarity of the potentials for 3 ohm will be plus and minus, because current is flowing in the downward direction. Now here, to calculate its potential, if we are moving something like this, negative to positive plus 3 into I2. And how much is the I2? Which is 0.25. Then negative to positive, which is plus, its potential is a 4.5. Then we are traveling towards a no element, which is equal to 3 into 0.25. Here 3 into 0.25, which is equal to 0.75 plus 4.5, which is equal to 5.25. This is 5.25 volt is the value of the VTH. And if we know the value of the VTH, next we can find out the value of the RTH, that is Thevenin's equivalent resistance. Its figure will be something like this. The step number 3 is the calculation of the RTH. For the calculation of the RTH, load resistance should be removed and all sources must be replaced by its internal resistances. Then figure will be something like this. Here is A, this is B, resistance 3 ohm, 6 ohm and 6 ohm. Now these three resistances are parallel. Then we can find out its parallel combination at once by using formula 1 upon R is equal to, this is 1 upon R is equal to 1 upon R1 plus it is 1 upon R2 plus it is 1 upon R3, which is 1 upon 6 plus 1 upon 6 plus 1 upon 3, which is equal to this is 1 divided by 6, 1.16. This will be 0.166 plus 0.166 plus 1 upon 3. This is 1 divided by 3. It is 0.33. This is 0.33, which is equal to plus 0.166 plus 0.166. It is 0.665 is 1 upon R. Then R is equal to its reciprocal. That is 1 divided by 0.665, which is 1.5 ohm, is the RTH. This is RTH. This is RTH again in this direction. If we know the VTH and RTH, otherwise simple trick will be parallel combination of these two. 6 into parallel with 6, that is 3, and 3 is parallel with 3, its half value, that is 1.5. That will be the answer. Then here, if we know the value of the VTH, value of the RTH, then this complicated network will be replaced by the Thevenin's equivalent network. This is step number 4. Thevenin's equivalent network. Now here, this is the Thevenin's equivalent network, and reconnect the load which is removed in the first step, which is 10 ohm. This is 1.5 ohm RTH, and which is 5.25. Now here we can calculate its load current, that is IL. VTH 5.25 divided by RTH 1.5 plus RL, which is 10, which is equal to. Here in this case 5.25 divided by 11.5, which is equal to 0.456. this is current 0.456 amperes is the current flowing through the load resistance by using Thevenin's theorem. That's it for this kind of this things. Means somewhere the network is complicated, then we should have 3 loops or 2 loops. In that particular case, we have to use a different techniques, that may be the mesh analysis, nodal analysis, direct inspection method, and so on, to calculate its current. That is about this particular problem. Now here, in this particular case, we will find out the Thevenin's equivalent network for this given figure. Now here, already load resistance is removed and figure is given to us, and here in this particular case, this voltage may be, here it is 10 volt, and in this case we are planning to calculate its network or its equivalent network. The procedure is the same. First calculate current in this loop, which is I. Here if we are applying the KVL, and we are calculating its current, KVL will be, it is plus 10. We are traveling from this point in the loop upward direction, negative to positive plus, positive to negative, that is minus 10i, then minus 10i, then minus 5i, which is equal to 0. Means indirectly this 10 is equal to 25i, or I is equal to 10 divided by 25. This is 10 divided by 25, which is equal to 0.4. 0.4 amperes is the current. If we know the current, then we have to find out the value of the VTH, which is equal to. We will travel from the B towards A. Now here may be the issue. This current only flows in this resistance because there is no back path. And if this current is flowing in this direction, it will be the plus, this is minus. This current will not come into this loop because there is, if that current is coming toward this, there is no back path for the current. That's why such chance is not there. If we are traveling from B, first voltage is 0. Then we are traveling in the upward direction, negative to positive, which is a plus, its resistance is 10 into its current, which we have calculated 0.4 amperes. Then we are traveling towards A, positive to negative, which is minus 6 into its current, which is 4 amperes, which is equal to, that is 10 into 0.4, which is 4 volt, then minus 24, which is equal to 20 volt. 20 volt is the value of the VTH. And if we know the value of the VTH, then we can find out its value of the RTH. For the calculation of the RTH, this complicated network, load resistance is already removed. This is voltage source replaced by 0 resistance. This is current source replaced by the infinite. This figure will be something like this. This is figure for the calculation of the RTH here. This is A, and here B, 6 ohm here. This is 4 ohm, 10 ohm. This is 10 ohm again, and this is 5 ohm. This is replaced by infinite, means this terminal we are keeping open in the air, that is nothing but replaced by the infinite resistance. Now, these two are in series. Figure will be something like this. Here is the A, this is the B. 6 ohm, 4 ohm, series combination 15 ohm. This is 10 ohm. Now here, final figure will be something like this. Here is A terminal, this is B, 6 ohm, 4 ohm. And parallel combination of this is 15 into 10 divided by 15 plus 10, which is 25. That is 150 divided by 25, which is 6 ohm. 6 ohm. Means here, this is the RTH, resistance between the terminal A and B. That's why here, this RTH is equal to 6 plus 4 plus 6, which is equal to 16 ohm. And if we know the VTH and RTH, this will be the final figure or equivalent network. RTH.